right. So I'll wait for 1 or so minutes for the screen to appear. And I need your help, guys, just to confirm that you can see and hear me. Perfect. I can see the screen right now. All right, guys, if you can hear me, please type something in the chat window. Yes, excellent. Thank you very much. So welcome back. And let's all start our new exciting webcast for today about OpenSpace, an open source astrovisualization framework. So let's start by introducing our amazing and great guest speaker for today, Dr. Alexander Bock. So Dr. Alexander Bock is currently a Sloan Data Science Fellow with the Center for Data Science at New York University. Since 2011, he is a PhD graduate student in the field of visualization and interaction at, well, that's hard to pronounce, so probably Dr. Bock is going to correct me later, Linköping University in Sweden. In 2015, he was a visiting research scholar with the Community Coordinated Modeling Center at NASA's Goddard Space Flight Center in the USA. He is also the development lead on the open source astrovisualization software OpenSpace, developed in collaboration between Linköping University, the American Museum of Natural History, NASA, New York University, and the University of Utah. Dr. Bock was awarded 2014 and 2015 with the Best Scientific Visualization Poster and 2017 with the Best Scientific Visualization Paper Awards at the IEEE Visualization Conference for his work in the field of astrovisualization. So please, let's all welcome Professor Bock.
Thank you very much. Well, professor is a bit premature, but yeah, so it's Linköping. I know it's a bit of a difficult thing to pronounce, but
my bad.
People will understand what you mean.
Cool.
All right. Let me bring up my screen, and I'd say let's start right away. Okay, so for everyone who's listening and wants to follow along and has a decently sized internet connection, the links to the software are right now on screen. If you want to compile them from scratch from the GitHub repository, that is fine as well, but that might take a bit longer. So we just recently presented OpenSpace at the Aztec conference, which is the Association of Science and Technology Centers, which was hosted in San Jose. And for that, we released a new pre-release version, which includes all of the data, and all of the things that I'm going to talk about today are included in that build. So whoever wants to download that and follow along, feel free. If something is not working, feel free to drop that in the chat window. I'm looking at that from time to time as well. Or otherwise, just drop me an email afterwards. It should be pretty easy to find my email address. Okay, so what I want to quickly start by is first go through a couple of slides introducing what I'm going to talk about, and then afterwards give a very hands-on example of what are the different things that we can actually show within OpenSpace and what we're currently building on. Well, thank you for the introduction. And as you said, we're developing a large-scale astrovisualization software. In this case, we want to contextualize a large variety of data sources. So in the pictures on the bottom, you can see 3 of the examples of what we have done so far. And our goal with this software is to have a 3-pronged approach. So we want to increase the amount of knowledge in the public, which is done through dissemination of scientific data. We want to provide a research platform for visualization science itself, which part the poster and the paper was about. And then also in the 3rd part, develop a science tool which can be used by actual domain scientists in order to further their field and develop new insights in their respective fields. So this, for example, in the lower right, as you can see, this is a visualization that was done by Emil Axelsson and his thesis together with Thomas Rosin. And it's about space weather simulations that were done with the CCMC at NASA Goddard. So, and we're now currently in the process of bringing the software to them to actually do research, well, on their data. Also, as you mentioned, this is a very collaborative process. So it all started with Linköping University in Sweden, where I did my PhD. And it very quickly, well, from the very beginning, the American Museum of Natural History in New York was involved. And these two institutions together paved the way through a former project that, well, was redesigned now well, not redesigned. Let me rephrase that. The Linköping University and American Museum of Natural History back in 2000 started a previous collaboration, which ended up with a software called UniView and a company called Skiss that is selling that software. And well, when I started, we wanted to approach the problem in the same way, but doing it in an open source software this time. And this is what OpenSpace became. Beginning of last year in 2016, we were awarded a NASA CAN award for community outreach. And this brought the New York University and University of Utah as US-based institutions into the fold. And then finally, as I mentioned before, Goddard Space Flight Center, the Community Coordinated Modeling Center, was involved from the very beginning in this endeavor. So we started with the software. The very first lines of code were written back in 2014, beginning of 2014. And as I said, it was from the very beginning, it was the idea to have this as an open source, community-driven platform. So right now it is under MIT license, so everyone can do with it whatever they want as long as they put the name on it. And we're very eager to get more information from or not information, but also code from the community in order to strengthen this application and make it useful for everyone. So we have it right now on GitHub, and the link is on the screen. Feel free, or anyone can feel free to download it and make use of it. So right now we're very close to scratching the 5,000th commit, which is very exciting. And we can down in the bottom you can see the commit history. So it has been going on for quite a while, and some of the milestones that I'm going to talk about in this presentation are, you can see the peaks in the commit messages in the bottom. So for example, the right dead and center July, that is July 2015, was the New Horizons flyby at Pluto. And there was a lot of crunching afterwards, and then a few months afterwards, where not much happened because everyone needed to recoup from that stress. Some more housekeeping. Up in the top right, the QR code is the same download link that was on the first page, which is also the Google short link there. We have our webpage is openspaceproject.com, and as I mentioned, we just released our 15th pre-release version. Which includes all of the data and also has a little Mars package on it, which I'm also going to show a bit later. Our YouTube channel is OpenSpace software, and we're currently uploading once in a while new videos and just showing off the features of the software. So feel very free to join that as well. And our Twitter handle, obligatory. Okay, so what I was thinking of for today was giving a very brief overview about the capabilities of the software. I'm going to do this by switching relatively rapidly between slides and live demos, because everyone thinks, well, live demos are much more interesting. So I'm going to talk first about different display systems that we support, then talking about examples of mission visualizations that we have done in the past, going a bit into the volumetric rendering, and finally, the planetary surfaces and going beyond the solar system, and all in the context of how is it possible to manipulate people's data or ingest people's data into our software. So if we start with the display systems, we make use of a also freely available library called SGCT, the Simple Graphics Cluster Toolkit, which essentially handles everything for us when it comes to rendering different modalities, different projectors, multi-projector systems, and so forth. So as one example, we have very regular flat screen rendering, as you're going to see today. Especially for planetarium softwares, it is very useful to render out dome masters in fisheye rendering. So this is essentially a 180-degree view of, I don't know where I took this picture, but of within OpenSpace of the Earth. So in order to imagine how this image works, we have the center of the dome right in the center of the fisheye, and the rim of a dome in the planetarium around the corner. And then essentially this fisheye is stretched over the entire hemisphere. Thanks to ongoing collaboration with the Illuminati, they provided time for development of integration of a library called Spout, which allows us also to ingest this into recording software such as open broadcast software. So all of the videos on the YouTube channel, you're going to see all of those were recorded using this setup, and we're very grateful for them for providing this information, for providing the software, the code. As I was mentioning earlier, with SGCT, we have the ability to render multi-projector systems, in this case, multi-display systems or power walls. This is a setup found at the University of Utah, the Scientific Computing and Imaging Institute. It's a power wall of 36 displays, which are powered by 9 separate computers, each of them rendering one column. And essentially, the library takes care of synchronizing images between the displays and making sure that when one computer does something, it's networked to all of the other ones, and making that possible. And then finally, also, of course, we want to render life into planetariums, which is a whole different problem of that includes warping and meshing, which I'm not going to go into because that's very technical detail. But I'm very happy to answer any questions that come for that. When it comes to interaction techniques, Jonathan Bosson, who's a master's student at Linköping University, just finished with his thesis, and it was his work that brought us integration of touch tables into the fold. So here we can see him interacting with the touch table. He was doing his thesis at the University of Utah, so this is recorded there. And if we jump ahead a bit, can see how, well, essentially now we can start touching the planets and moving with gesture interaction. And part of his thesis was to determine whether it's possible to use this form of direct touch interaction in a planetary context or not. So when we're very close to a planet, the movements of the hand, or the movement of the planet, follow the movement of the hand, and well, that doesn't really work when we're far away. So that's the contribution here. Furthermore, this is rendered in the dome in Norrköping, which is in stereo, which is why the background image is a bit blurry. So you see basically images for both eyes. And here we're interacting through a Kinect and controlling the application that way. So this was done through a collaboration with Andrei Krekov from the University of Duisburg in Germany, who developed a very flexible UI called Morphable UI, which allows us to ingest multiple interaction systems. Okay, so after this very brief overview of display systems and interaction, I was thinking of just going very briefly through the ideas of how we're going to set up an OpenSpace instance and how we can control that. And for this, I'm going to jump out of the presentation. And so if anyone has downloaded it, we're going to find a folder somewhere like this. And it essentially starts all with this OpenSpace.config file. So if we start that up, we'll find that all of the configurations files that we do in OpenSpace that we are using are essentially Lua scripts that get executed at runtime. So if anyone can read Lua scripts, then you'll be very familiar with what's going on. But for everyone else, essentially this function returns a table of settings. And as you can see, there are a couple of settings that are available. However, the two most important ones are this SGCT config. That's the same SGCT as the windowing framework that we're using. And in this case, essentially what we're saying is that we want to generate a single screen window of a resolution of 1280 by 720. Right down here, commented out, we would generate a 1920 by 1080 and so forth. So by changing this, we can very easily switch from a single screen rendering to a fisheye rendering and vice versa. Second important, or maybe even the more important one, is the scene tag. So in OpenSpace, whenever we start up the application, we're loading a scene which contains an entire scene graph of objects that we want to look at. In this case, we're looking at the default scene, which is, no surprise, our default, which basically includes all of the basics of the solar system and beyond. But then we also have the New Horizons for the New Horizons Spacecraft, Rosetta, OSIRIS-REx, and an example of rendering satellites. But it's very easy to generate new scenes if there's new data. So, for example, for Juno or some other missions. So with the default scene and the regular rendering window, if we start up OpenSpace in the bin folder, we have OpenSpace. And if we bring up the console, because it takes a second to load all of the data. So now we're initializing the entire scene graph that is at the back. So we're showing all of the 8 planets. We're rendering our sun and our solar system, the Milky Way, and everything until the edge of the universe. So that obviously takes a while. So by now we're almost done with the heavy things, and we should be seeing the rendering showing up any second now. So here we are at Earth, and before going into any details, I want to just mention that if you get this far, the user interface is hidden behind the F1 key, which will bring us here, and now we have access to all the different instances of what's going on with OpenSpace. So for the default scene, we have marked a couple of nodes as being important. So for example, Earth, and we can start having a look or disabling the Earth and playing around with that. And I'm going to go into the details of that when we get to the planetary rendering. The scene graph, as I mentioned, is hidden behind the scene graph properties, which gives us access to a tree-based layout of what we are currently having in the scene. So for the solar system, we have all of the different planets. In the Milky Way, we have a large set of data sets which come from the Digital Universe, which is a curated data set by the American Museum of Natural History. So here, for example, we have the stars that we see in the background and can play around with those. And then finally, in the universe, we have all of the galaxy surveys and so forth. Another kind of neat thing is that, well, loading images, because sometimes during explanations, it might be necessary to get some new images. So one of the things that we define, if we go back to the OpenSpace config, is next to the SGG config and the scene, we have a set of paths. And one of them is OpenSpace under data, which gives us access to this folder. And here we have conveniently a couple of test images that I want to just play around with. So if I want to add a local image, I can just say we want to have OpenSpace data test2.jpg, and we get a QCAT because it's the internet after all. Or alternatively, if we just want to have from the web, let's just take this one, take the URL, going into add online image. And here we have an image that was just downloaded. So this is very useful for educators that want to start using online resources to augment presentations, especially in planetarium surfaces where you don't normally can just open up a browser and show an image. OK, so with this, let's switch back to the presentation, because I want to go into the first concrete example of what we have done. For mission visualizations, the idea was to present how research based on spacecraft is actually done, rather than just showing the final results in the end. So our first example with this was the New Horizons spacecraft, which flew by Pluto back in 2015. So all of the mission was entirely planned almost a decade in advance. And it was essentially just pre-programmed to record lots and lots of images and data while it was flying past in the maybe 6 hours or so that it took. And it is very interesting for the general public to understand how this is actually done, rather than just seeing the final images of the heart, for example. I mean, granted, it's a very pretty image, but if you see it happening live, quote unquote, it's a much more compelling information. So for this visualization, we were mainly focusing on the LORI camera, which is water spacecraft, which stands for Long Range Reconnaissance Imager. There's another R in there, which eludes me right now. But it's essentially a pretty large telescope that is on board and is taking grayscale images of the surface. So we wanted to show what that camera was doing during the flypath. So this is something that comes out of the mission planning software. So here you can see the planned images that the LORI spacecraft was taking, would be taking at 10:16 on July 14th. And each green rectangle is one image that was going to be taken against the backdrop of a Hubble image. So this is maybe very informative for mission scientists, but in general, it is not very interesting for the public to look at, because you're missing the entire context of what is happening, of where is the spacecraft, what is it doing, how does it actually take multiple images, because the camera is not really movable, and so forth. So what we did with the help of Michal Markinkowski, another student from Linköping University, was implementing a projective texturing approach. So this was presented by Everett from NVIDIA back in 2001 already, and it essentially treats the camera as a projector and projects the image onto another body. So in this case, here we can see a flat image being stretched out over the planetary surface. And if we do that for multiple images across the planet, then we can actually show how the base map that we now have, and for the foreseeable future, the best version that we have, was actually created. And let us jump into that as well, because why talk about it if I can show that as well? So if we go back to the OpenSpace config, now we're actually going to touch the scene file, and we'll just comment that out and comment this one in. And when we start up, we'll start loading the New Horizons scene instead. This contains some of the solar system that is necessary for the context, but mostly is concerned with the New Horizons data, which includes information from so-called SPICE kernels, which is another NASA library, which essentially gives us information about the location and the orientation of different bodies and spacecraft in space. So here we start out. We start at, I just pressed the space bar in order to stop the time. We start out on July 14th, so the day of the closest approach, at 8 a.m. UTC. The yellow line that you're seeing is the trajectory of the New Horizons spacecraft, where each dot is 15 minutes, has 15-minute intervals. So we can actually get a pretty good feeling for, no, each dot is 1 hour intervals. So we can get a pretty good feeling for how fast the spacecraft was actually moving through the system. So we're starting at 8. The closest approach was somewhere close to 12. And, well, another 5-6 hours afterwards, we're essentially left the system again. So at the time, it was flying past the system at about 14 kilometers per second, which is quite impressive. So if we zoom in, we can actually have a look at the spacecraft. We have to zoom in a bit more because space is really big. And here we are. So here we have the New Horizons spacecraft. The giant Rex antenna, which sent us back all of that information with a terrible bandwidth. And down here we have the long range reconnaissance imager. which was taking images. We have the SWAP, energy particle, ultraviolet spectrometer, and near infrared camera. And then finally back here, we have the radioisotope generator, the thermoelectric generator, which produces all of the energy for the spacecraft. So what I was mentioning before with the projective texturing, we can see down in the lower right, because this is actually the viewpoint of the LORRI spacecraft, of the LORRI instrument. So we're seeing it right now pointing roughly in the direction of Nix. But if we start playing with the time, can actually see, okay, it's not actually the camera that is moving, but the entire spacecraft is pivoting around. So there are, I forgot the numbers, a number of reaction wheels, reaction thrusters on the spacecraft, which fire in order to rotate the entire spacecraft in order to take the pictures, which was part of now the limitation of what they can do with the future, because that takes fuel and that is very precious. So now we can see how the instrument is sweeping across and actually now starting to aim at Pluto. And with the press of the, if we open up the user interface, now we can start focusing on Pluto and zoom in, and we should be just in time. So as you can see here, this is the final image that we have right now. But now we can see how this image was being taken. So we have the instrument here, and just again, down here on the left, you see how much time is left until the next image is being taken. So I'll just start playing the time, and you can see how the individual images were taken and essentially combined into the image that we now have. So if I speed up time a bit, you can see how the spacecraft is aiming at the planet and taking individual images. So this is how science is being done in real time. Well, real time, quote unquote. So right now we're moving almost at a minute per second. And here we have one of the earliest full Pluto mosaics. So we actually make a point of not showing, or of actually showing the boundaries between the images, because this is kind of part of what we want to do, and how the main work afterwards of creating a fully fledged image was being done by the scientists themselves. So if we zoom ahead in time a bit more, the next image campaign was done at 10:10. Here we begin. So there's the spacecraft, and well, now that the spacecraft is much closer to the planet, we can actually see that the footprint of the image on the surface is much smaller. So we're going to get a much higher resolution now. So if we zoom in, we'll be able to see much more detail what's going on. And this is also the reason why sometimes with some of the outer solar system objects, there's such a great variety of resolutions. So if we look at the limb, for example, there we only have the full image from earlier, but here in the center we have a much higher resolution now. So we're going to see actually the difference in resolution. Continue on. Going to get another sweep across, and the images are getting gradually better. So this is how the Horizons was flying past Pluto and taking pictures of Pluto and Charon. So we're taking lots of images, which is a bit taxing right now. And now we're almost, we're a bit past closest approach. I was flying past Pluto about 1/10 of the distance between the Earth and the Moon. Just to give in context what great instruments there were on board. Okay, so this was New Horizons. Based on this, we held a hackathon in the American Museum of Natural History also last year, where we had 2 teams that were participating in order to visualize the Cassini mission, which has now unfortunately ended, and the Messenger mission. So this is a video of one of the teams that managed in just 2 days, without any prior experience, to generate this level of visualization. So if we jump ahead a bit in time, so we see a volumetric rendering of the solar wind as it is deflected by the surface of Mercury, and we have the mission actually orbiting around the planet. So this is just a screen grab, so you have to excuse the poor image quality. So this was done, as I said, by a team of about 10 people in the course of maybe 12 to 16 hours of work. All right, to the next part, which is dealing with volumetric data. And in this case, I'm only going to talk about the space weather simulations that are done at Goddard CCMC. So here we have a simulation called ENLIL, which simulates the entire, or in this case, the entire solar system. So this is a simulation that was done to coincide with New Horizons' closest approach of Pluto, because as you might have seen, the New Horizons spacecraft has a solar wind measurement device on it, an energy particle measurement, which measures what is essentially left of the solar wind out at Pluto. And the idea here was to render the data volumetrically and compare that with what the mission actually says it did, or what happened. So in order to, and by comparing these two pieces of information, you can learn a lot about what the physics, plasma physics in the solar system is like, especially this far out. So as you saw before, that was a single time step, but here we have a volumetric rendering of the, I think, a month around the closest approach. So you have the Pluto orbit in the blue line further out, and the ENLIL, which is basically moving like a sprinkler from the inner sun out to the outer solar system. So the sun is constantly putting out highly energetic particles, which interact, in the case of Earth, with our magnetic field and give us the beautiful northern and southern lights, but also can damage spacecraft and satellites, as has happened in the past. So predicting this is a pretty important deal. The missing parts of the data in the top and bottom is just missing information where we're not that sure about the conditions. So we'll leave that out. So we did a rendering of that. Unfortunately, I don't have the data here because it's quite heavy, but we made that into a YouTube 360 video, which I'll just bring up. So this is also found on our YouTube channel. As I said, this is a YouTube 360, so I can just grab it and move it around, and we have the entire rendering here. So this was a program that was done in order to explain the science behind the solar wind. And here we had two of the mission scientists, Leila Mays and Masha Kuznetsova, who were talking about their respective sciences and what is happening in the solar system during storms and so forth. So as it's a 360, if you have a virtual reality headset, you can look at it in VR and look around, which is pretty cool. But well, on flat, it's also pretty interesting. So here right now we have the sun, and if I go back again, okay. So the image in the background is being taken by 3 separate satellites, Stereo A, Stereo B, and the SDO, and we merged those into a contiguous background image, very similar to the approach that you saw with Pluto. And here in teal, we have now the field lines that are being simulated on the surface of the sun. So along those field lines, magnetic energy or particles would travel, and these would become eventually the source of solar events. And then later, just have to look at the timestamp. We're looking at a simulation of the magnetic field around Earth. So we have the sun all the way there on the left, and now here we have our magnetic field around Earth protecting us. So the pink line is an example orbit of a geostationary orbit, and in the yellow field lines are the ones that are connected to Earth. and are being deformed by the solar wind as it's being blasted towards the Earth. And well, especially in this case, the 360 brings a lot of benefit as to be able to just essentially look in every direction and get a really immersive feel for how big this field really is. So this video is a pretty good example of what is good about this software in terms of public dissemination, because we have the ability to show this to other people alongside the original explanations that were given by Leila and Masha during the presentation at the Hayden Planetarium in New York at the American Museum of Natural History. And well, having these archived for the future is probably very beneficial. Okay, if we move on to another topic in terms of planetary mapping. So as you saw in the very first example, we render planets. We make use of yet another library, which is this called GDAL, the Geospatial Data Abstraction Layer, which allows us to render very high resolution images of planetary surfaces. This is done by separating planets into trees. So as you can see in the lower right, we have the entire planet. This is split up into four quadrants, or each half is split into 4 quadrants. And then depending on how close we are to the planet, we can subdivide each of those quadrants further and further and get higher information. And essentially access all of this data through a web API, which frees us from pre-downloading the entire data set, which can be quite heavy for some planets. So here we can see the tree in action. So we have the camera in the lower bottom, and for those areas where we're very close, we need a very high resolution. So we have a very high subdivision. But for the horizon, we don't really see that much detail anyway, so we can get away with much higher resolution. So if you take each of these squares is 256 by 256 pixels. And essentially by making the square smaller, we get a higher pixel density, thus a higher high information density. This can be done with a number of separate layers. So we have color layers, as you saw in the previous example. By treating height information as a grayscale image, we can deform the terrain up and downwards to create a 2.5D height field, and I'm going to show that in a second. There are a couple of overlays. We have the ability to render a separate texture on the night side, and also use a binary mask for reflection. So here you can see that the sun is reflected of the water, but not of the land as it should be. And I was also thinking of giving a short example of this. So if we go back to OpenSpace config, this is all hidden behind the default scene. And if we start up, now we're going to load all of the data again. So this example includes Earth, some information about Mars, which I now forgot to include, but we can do that afterwards. And as I said earlier, all of the rest of the universe. So right now we're loading the SDSS, which is the Sloan Digital Sky Survey, which is the biggest of the data sets, which includes, I think, a couple of million galaxies. So here we are. If we increase the size, and we can have a look at Earth. So bring up the menu again. We don't really need this shading. So now we're loading the NASA GIBS, that's a global image browsing system, which is a service from NASA that provides us with satellite information from the Earth. So this is a current, I think probably yesterday, image of the Earth. So we can see, I mean, right now in New York it's pretty cloudy, so this probably fits. but it also includes a lot of other data. So if we start zooming in, we'll now start downloading images from the web. And now we're switching over to a different data set, which is produced by Esri in California, which is a global map that is curated so that it doesn't include any clouds. So basically, it's an entire year's worth of image data. So if we zoom in, you can zoom into Salt Lake, for example, and here you can see the images being gradually downloaded from this case, Esri's servers. So if we tilt up, you can start seeing the beauty of Salt Lake. And with the mountains in the background, as I said, essentially all of the height fields are grayscale images, so they can be used, they can be handled by the same mechanism. So if we go to a different place, let's pick the Grand Canyon. This is pretty drastic formations. So you can zoom in. You can see, now if I zoom in too quickly, we can actually watch the download happen. Atmosphere was implemented by Jonathan Costa, who spent quite a while to get it physically accurate. So, for example, if we start looking at the west, you can also see that it's not just physically accurate, but also really pretty. If we play around with the time and see when the sun starts setting, you can start seeing a nice sunset as it happens. As I said, this is physically correct, so as long as we know the parameters of the atmosphere, we can simulate now sunsets and sunrises on different planets. Zoom up, out again. So, as I was mentioning, we want to give access to a lot of different data sets. So, if we bring up the user interface again, we have a separate menu for the globe browsing, which gives us access to all of the data sets that NASA GIBS is serving. So right now we're going throughout to one of their web APIs, and scrolling down, you can see that there's a lot of data sets available. So for example, if we look at, I don't know, something, I don't know what any of this means, but let's take the carbon monoxide and add it as a color layer. And now, again, going out to the web services, and now we're probably seeing the concentration of carbon monoxide in the atmosphere. Or saw something with cloud earlier. Yeah, the cloud top height, for example, which gives us information about the height of the clouds, which matches with the underlying image. So I'm pretty confident that that works. Another neat part is if we go back. So if we look at the VIRS layer again, as I was mentioning, this is today's image or yesterday's image. But if we go back a few days, so for example, going to October 1st, we can now get the information about that particular date. So it's downloading the images, and right now, unfortunately, we have to cache a bit of that. But if we start going around the time a bit, so now we have, well, essentially just 3 days, but still. So first the sun above us. And now we can go back in time and actually start looking at how the clouds are moving from a day-to-day basis. Same thing if we would be further away. That's a bit hard to see when it's rotating, but that's why I was moving closer in. So one of the other neat things with the new atmosphere is if we go to the day of the solar eclipse, which I hope I got right. Probably didn't. No. So ahead. Include the full simulation, not a simulation, but a rendering of what the solar eclipse looked like. So here we are back in UTC, which is why I was a bit confused. We see the sun, the surface, or the shadow of the moon moving across the solar, across the Earth. And if to show the shadow bounds of it. So this little black dot in the middle, this is the actual total eclipse path, or the positions on the Earth which are in total eclipse. So if you're lucky enough to be along this path around on the US, then well, you know what you saw. You can feel very lucky about that. Okay, one other quick thing that I wanted to show is the Moon and the Mars. And since I forgot to include the data, I'll need to show that and show how that is done as well. So I pre-downloaded a GeoTIFF file of the Moon, which we can include in here. So if we go to, let me do that again, go to Data, Scene, Moon, and then we have a moon.mod, which is yet another Lua script file. We can add another layer to our scene. So we want to have, in this case, it's Apollo 16. And I placed it on a disk here. This includes this GeoTIFF file, which is converted to a virtual raster table, which is done through GDAL. There's information online how to do that. It's a simple command, and loads that as a color layer on the Moon. And then finally, for Mars, on the webpage, there's another download for Mars data. And in here, I extracted this also locally. And just referencing those folders. If you download them, you'll get a CTX and a high-rise folder, and adding them like these will add them to the scene. Okay. With this, you can start this again. It's still the default scene, so that one works great. And now we can load the data sets again. So the GeoTIFF, I didn't try that in advance, but we could try loading that. Yes. Sometimes Windows has a bit of an issue with loading large TIFF files, but this is essentially the information that we have, which is the landing site of Apollo 16, the near field, the narrow angle camera view of it. So this was taken by the Lunar Reconnaissance Orbiter way in advance, way after the fact. So if we go to the Moon, which unfortunately doesn't take that long in the software. So here we are, and here we have the broad area of the landing site of Apollo 16. So if we go to the Moon and we enable the layer that we just added, here we have it. And now we can start zooming in and looking at, well, if you were looking at the image in it previously, you don't really have a good idea of what the context for it is and how large it is on the surface of the Moon. But now we can actually start having a look at that. Bring up the brightness a bit. So here we have two of the craters, one of them which they visited, and now we can have a look at what it actually, well, looks like in context. And also because it's another very good camera, right here we can actually have a look at the exact landing spot. So here we have the descent module that they left behind when they left the Moon. Here we have the footprint of the rover, and we can actually also see the rover tracks, a mission package, and further rover tracks going on to the distance. And they were covering essentially all of this area up until down here. All of this information is freely available, and well, this GeoTIFF is, well, 500 megabytes, so it's reasonably sized. But well, all of this data is online as well, so we wouldn't even need to download it, but it works. The last thing that I want to do in a solar system is go to Mars. So we focus on Mars, and we zoom over. And here we have Mars, also with a new atmosphere. And in here we have Valles Marineris, a large canyon on Mars. The background image that you're seeing here is a reconstructed image from the Viking mission, which has about 1 kilometer resolution, which means that each pixel in the image covers about 1 kilometer. But since that has been taken, we have gotten much higher resolution information. So if we enable an image called the CTX, which stands for context camera, we start loading that now in from Linköping University. And this, again, uses the same mechanism as we saw on Earth. In this case, we don't have a complete global image, which is why you see these stripes in there. It has been since filled up, but we haven't updated our map yet. But that's about to come. And now we can start going into Mars. So if we start zooming in, now the connection to Gibbs is much better than the connection to Sweden. So it's loading in a bit slower than that, but it will eventually kick in. The CTX, we also have a local image, which is included in the other zip file. So if we enable that, you can actually see what the resolution of the context camera is. So I was mentioning the Viking image has about 1 kilometer resolution. The CTX camera has a 6 meter resolution. So each pixel in this image is about 6 meters, or about a two plot garage. So it's called context camera because they were using it at the context to retrieve higher resolution images still. These are the high-rise images. So in this case, for example, in West Condor Chasma, we have one higher resolution image, which is right here. And if we enable a better height field for these as well, we can see why it's high, what the high in the high rise is. So the Viking image, 1 kilometer, context camera, 6 meter. The high rise image are done at 25 centimeter resolution, so about the size of a football. And here we can start seeing mountains that are about the maybe 300 meters high or so. And we can start seeing the actual terrain of Mars. And with 25 centimeter resolution, if there would be, this is below the resolution of what we just saw on the moon. So if there were Martians, we would definitely be able to see them. So all of these images are being taken from a satellite around in the orbit of Mars. And essentially, the height field information is being retrieved by taking 2 consecutive images from 2 slightly varying angles, and then basically by stereo reprojection, figuring out what the differences in the images are. And there are about 400 to 500 of these high-rise stereo pairs that have already been taken and that are available across the surface. I want to highlight just one more, which I think is very pretty. Ganges Chasma, which is over here. It's on the east side of. Unfortunately, I'm never been able to find this with the CTX on. So if we disable it, there we are. So here we have Ganges Chasma, which none of this is height exaggerated, so all of it is the real height. So here we can actually see how the Martian winds of Valles Marineris have swept around rocks in the valley itself and created sand dunes, not unlike what we actually see on Earth as well. And again, all of this data is free. And previously, there only existed a handful of softwares that can show that in 3D alone. But now, well, we're working, or we have worked on, and continue to work on an open source software that renders all of this and makes it available to the general public. With the last few minutes that I have, I want to leave the solar system and give a brief overlook of what other data sets we actually have included, namely the digital universe. You might have been looking at the stars in the background the entire time. These are not just 2D locations, but they're actually positioned correctly in 3D. So if we start zooming out and start leaving the solar system, we can actually start seeing how they resolve in 3D. But in order to do that, let us go to the screen space, to this scene graph properties, and enable constellations. So these are the constellations that everyone, well, is a bit familiar with, at least. If we find one that everyone knows, we should be able to find Orion somewhere. There's the Southern Cross, so we're just looking in the wrong direction. Oh, it's a problem of, yeah, there we are. So here we have Orion, Orion's belt, Orion's nebula. And so all of the constellations are connecting stars that are obviously at different distances. But from our viewpoint on Earth, we're not really seeing that. So we start zooming out. We can start seeing that we have one star moving here closer. This one is moving closer. And we can actually start seeing that thanks to the perspective distance that we now have, how the stars are oriented in 3D. And I personally think this is mind-blowing, because we all assume that the celestial sphere is exactly that, a sphere, and not a 3D structure of things. Here we start now resolving the constellation Hedgehog, our local neighborhood. Apart from the constellations, we also disable those. If we look at the Equatorial Grid, this is at a distance of about 80 light years. So this is how far we're now roughly away from Earth, which is how far our furthest radio signals have gotten out. So we can see all of the stars that are inside of the radiosphere have the potential to have received messages from us. And, one other interesting data set that we can look at in this context are exoplanets. So which of these stars actually we know have planets that could potentially listen to us? And essentially all of these we know have exoplanets around them. So these were discovered through using dynamic methods, so essentially looking at the light and how it changes when the planet moves around it. But then we also have the Kepler instrument, which has been looking at a particular location in the sky, mostly, until it broke, to get information. This is not it. This isn't it. This isn't it either. This is the main location in which the Kepler instrument has been looking. And if we look at it from behind, you can actually see the grating in the instrument. That you can also, if we look at images from the Kepler, then we can see how this grating is in the actual image sensor as well. And well, since it broke, it had to start looking into different directions. And these are the other arms that I was confusing it with before. So these are exoplanets that are recovered through the transit method. So we're looking at a star, waiting until a planet goes in front of it, which causes the star to be slightly dimmer. And well, if this happens periodically, we know that there's something in orbit around the star, which is most likely a planet. And based on the sizes and the amount of dipping, we can estimate what the size of the planet is and what it's made, or what the atmosphere is made of as well. So out here, we can have a look at other different information. All of these are in our own Milky Way. So now I enabled the planetary nebula, open clusters. You can look at pulsars as well, which all form the plane of our Milky Way. But what we can have a look at next is all of the nearest galaxies. So here we have our Milky Way. Here we have our closest dwarf galaxies. Somewhere over here, we have Andromeda over there. And if we start zooming out more and more, so now, instead of stars, each point in the background is now an entire galaxy, color-coded by density. These are a few of the data sets that we had to wait for in the beginning to load, which is all point clouds, but still, it's a lot of data. So this is all of the galaxies in the Tully catalog. But then we can have a look at the Sloan Digital Sky Survey, which reaches out even further and shows us some of the large-scale structures of the universe. You can also see that we actually haven't looked in all directions equally. So we have the northern hemisphere with lots of telescopes, and in the southern hemisphere, we only looked in certain directions. If we go further out, we can also have a look at quasars, quasi-stellar objects, even further out. Now we're maybe 1 billion light years, 2 billion light years away from Earth. And out here, the last thing to look at is the cosmic microwave background radiation, which is the echo of the Big Bang, which is essentially a sphere that surrounds all of us, and we'll never be able to pierce through this. So this is just a very brief walkthrough of the different extrasolar data sets that we have. And while I start zooming into the solar system again, if there are any questions from anyone, I'm very eager to answer those regarding the software and or the data.
Wow, thank you very, very, very much for a great and wonderful presentation. I mean, the demos are amazing. To be honest with you, I don't want to speak right now because I want people to keep watching the demos. It's really beautiful. So please, guys, if you have any questions, feel free to type them in the live chat here on YouTube, or you can type them on the Meetup website, and I can send it later to Professor Bock. But to be honest with you, I have a question, but because we're running out of time, would you please answer this question in around like 30 seconds? Thank you very much. So since this meetup is about evolutionary robotics and your topic is astrovisualization, do you see any possible collaboration between the two fields to simulate a robotic behavior in space?
I absolutely think so. That's why I started out with the mission visualization, because I mean, essentially they are robots, right? I mean, they're doing everything automatically. The light delay from Earth to Pluto, for example, is 4 hours. So there is no way we could ever live control this. And I think this also is shown on Mars with the Curiosity rover. And being able to explain to people how difficult this actually is, I think there's a huge benefit in visualization to be able to do this. And I think OpenSpace would be a good way to do that in order to explain it to the people, as we've done with New Horizons and as we're going to do soon with Curiosity.
Awesome. Thank you very much again. And if there are any questions, I'm going to forward it to you, or people can reach out to you because you shared your contact info earlier. Thanks.
I'll just bring it up again.
Okay, awesome.
And yes, thank you for inviting me.
Thank you very much for being here. Guys, see you next month in more topics. Have a wonderful rest of the day. Bye-bye.
Bye.